What you see is a beautiful rural landscape with a flock of Dorper sheep and two alpacas. What is a little harder to see is the large amount of invasive weeds present which are causing major problems to the Australian agriculture industry. The title of our paper is Efficient Herbicide Spray Pattern Generation for Site-Specific Weed Management Practices Using Semantic Segmentation on UAV Imagery. My name is Bo Hobber and I'm a student from the University of Sydney. I was assisted on this paper by Safak Akinci of Elsassen Electronic Industries, Ankara, Turkey, and Ali Goktegan from the Australian Centre for Field Robotics, University of Sydney. Invasive weeds are common in rural areas. These weeds quickly overrun regions of land and reduce yield from crops. They are noxious to animals, leading to a variety of diseases or mortality. These weeds are irritating to people and some animals. As reported in 2018, 61% of Australia's entire landmass is used for agriculture. Of this landmass, 7% is covered in invasive weeds. This is shaping up to be a very expensive problem, costing farmers up to 5 billion Australian dollars per year in lost production and control costs. Weed eradication requires farmers to single-handedly spray individual weeds with lackluster tools or entire fields of machinery. This is expensive, damaging to the environment, and time-consuming. The motivation of this paper is to reduce the amount of area which herbicide is required on through site-specific weed management. This paper attempts to solve how deep learning with UAV imagery is used to find efficient herbicide spray patterns. The targeted weeds will be capeweed, thistle, Patterson's curse, and stinging nettle. The workflow to accomplish this is summarized into image collection, image and data extraction, image preparation, semantic segmentation, herbicide maps, frame correlation, and mapping. The first step was to obtain data of weeds in a rural environment. The waypoint following tool was Litchi, and the UAV being used was the DJI Mavic 2 Pro, which obtains 5,472 by 3,648 pixel resolution images. The ground sample distance, GSD, is calculated from the congruent triangles formed between the UAV camera lens and the ground. This method converts 1 pixel to a physical distance. Images were taken at an altitude of 10 meters, which translates to a region of 12.24 meters by 8.15 meters. The elliptical WGS-84 World Geodetic System was used as the Earth reference frame to find the latitude and longitude coordinates of the current UAV position, depicted by the white dot. To create a new waypoint depicted as the black dot, the change in position is utilized to solve the new latitude and longitude coordinates. This can be extended to create full path plans. These waypoints are then mapped to ensure the entire field is scanned. Regions of overlap are introduced to ensure every location is sufficiently imaged. Then the displacement is measured to convert meter-based increments to latitude and longitude, finally allowing the next waypoint coordinates to be determined. The coordinate reference frames of the UAV allow the eventual geotagging of weeds. The first reference frame corresponds to the UAV's position in the world, and then its inertial frame relative to the ground and north. The UAV's respective body frame is then considered. Pitch, roll, and yaw are determined through a set of rotation matrices by comparing the body frame to the inertial frame. Pitch and roll determines the orientation of the UAV, whilst yaw determines direction. The gimbal and camera are related with respect to the UAV. The camera is positioned to face the ground at all times. The final transformation relates objects in the image to the world. Initially, 83 images were labeled in the ground truths, with a total of 10 classes. These original images are then split into 224 by 224 pixel sub-images to increase the amount of data. In total, this creates 33,020 overall images. Data augmentation is performed with both color and position augmentations being implemented. The data is split into 70% training, 20% validation, and 10% testing. 40 epochs and a batch size of 64 is used for each model's training. Loss functions are explored to offset the extremely underbalanced data by prioritizing the less dominating weights. The most suitable loss function for the data was categorical focal loss. In the image, using loss functions on the ground truth and prediction data of a grass and a thistle sample demonstrates categorical focal loss's effectiveness at reducing loss on imbalanced classes. The models used consist of an encoder based on either VGG16 and ResNet50, whilst the decoder consists of segmentation-based models. In this example, UNet was used. The best model was ResNet50 Segnet, which provided adequate precision for all weed classes. Precision is important as it matches positive detections to the ground truth. The precision of Thistle was 56%, Capeweed was 68%, Stinging Nettle was 73%, and Patterson's Curse was 77%. Here are some predictions evaluated by the semantic segmentation. Exact alignment is not required, only the detection. Finally, the predictions of the machine learning were extended to full-sized images, through separately predicting each individual sub-image and then concatenating. Weeds are often found in groups, and eradication techniques have a limited spray size. This spray pattern is normally cone-shaped. Making the semantic prediction 100% accurate to the ground truth is not required and unfeasible. Thus, this paper proposes a new method of creating a herbicide map which accounts for real-world spray size and the clustering of weeds. Spray size relates to the width created from spraying weeds at a direction perpendicular to the nozzle. This method creates a triangle, which can then be extrapolated to form a simple trigonometric equation. Based on nozzle size guides and the weed sizes being explored, spray size was initially set to be 0.2 meters. Weeds are often found in groups, and eradication techniques have a limited spray size. Making the semantic prediction 100% accurate to the ground truth is not required and unfeasible. A represents the prediction image, and B is a structuring element. The size of the structuring element was determined through testing the accuracy, efficiency, and saved herbicide on the dataset. Morphological closures were used to increase the represented size of all weeds. This enabled weed clusters to be accounted for. As the structuring element increased in size, weeds became too clustered together and only small amounts of herbicide were saved, and alternatively, a decreased structuring element was ineffective at detecting weeds. The ideal closure in radius was 40 pixels. The major and minor axis lengths are found for every weed region within the morphological image, converting each weed representation into an elliptical shape. These correspond to the maximum and minimum vertices of the weed. Spray size is converted from a real-life measurement to a pixel-based measurement using the inverse GSD. The radius of the final region is equivalent to half the horizontal and vertical diameters of the regions with the addition of spray size. This method ensures that excess herbicide from spray patterns is not wasted. These circle regions are then converted into herbicide maps, which indicate the location of potential weeds. Herbicide accuracy corresponds to how many weeds are detected within the herbicide map. The herbicide saved in each image is represented by all the area that is not within the herbicide map. The herbicide efficiency compares the herbicide map generated from a ground truth. As spray size increased, the efficiency and accuracy improved, while herbicide saved decreased. A large spray region means more potential weeds are detected within the region bounds. Herbicide efficiency decreased during smaller spray sizes as less intersection is apparent between the prediction and the ground truth herbicide maps. The Euclidean distance between the herbicide saved and accuracy and efficiency was recorded for each spray size. The minimum value is selected from the range of sizes, with this value representing the most balanced spray size when accounting for saved herbicide, accuracy, and efficiency. This value was approximately 0.45 meters. The overall average accuracy of the entire dataset was 85%, efficiency was 93%, and 55% of herbicide that would have been used was saved. The herbicide saved in the table demonstrates that the system sufficiently saves a large majority of herbicide, even though the characteristics of each region of land change. Previously, the results of the semantic segmentation only provided the ability to detect and classify weeds. The results of the herbicide mapping demonstrate that this metric evaluation is not necessary as long as the actual weed cluster can be identified instead. Widely used methods completely spray fields with herbicide, whilst this paper's algorithm proposes a successful method which can perform site-specific weed management. Which one shows more green? This method reduces expenditure, time, and environmental damage associated with herbicides. Furthermore, the detected weeds locations also can then be converted into realistic maps. This is a useful feature as it allows the potential integration of GPS-based devices to perform eradication. This paper has successfully contributed a method to collect UAV aerial imagery and classify and detect the weeds present. Site-specific weed management was performed for the generation of herbicide maps. Geographic mapping of weeds provides useful tools for farmer interaction. The design of this weed detection and classification system has allowed for multiple future developments, including optimizing the herbicide maps to support different weed formations, extending the dataset to improve classification, and implementing herbicide maps using other weed detection architectures. Thank you for listening.